In this video, we're going to complete some examples to show how we use the angle sum and difference identity for cosine. So starting with our first example, we want to simplify the following expression. And the way we can do this is by considering the angle difference identity for cosine. And to make this more obvious, we're going to make a couple of dummy variables. So we're going to let some variable A equal our angle 5 pi on 3 and another angle B equal 4 pi on 3. And now if we make this substitution into our above expression, we're going to get cos A times cos B plus sine A times sine B. And now you can see that we have the angle difference identity for cosine, as we got cos A times cos B plus sine A times sine B, and we use the bottom operator, so this will simplify into cos of A take B. So let's write this down here. We get cos of A take B, and if we substitute our A and B values back in, this is actually going to equal cos of A, which was 5 pi on 3, take B, which is 4 pi on 3, and 5 pi on 3 take 4 pi on 3 is just 5 take 4, which is going to give us just pi on 3. So we get cos of pi divided by 3 radians. And now we can use our masterly table to simplify this even further to find what cos of pi on 3 radians is. So going along the cos row, and we want to go down the pi on 3 column, we're at the square root of 1 value, and so we're going to have the square root of 1 divided by 2, which is just going to give us 1 over 2. And so cos of pi on 3 is 1 over 2. And so the above expression simplifies into just a half. So that concludes this example, and now let's move on to our second. For our next example, we want to find the values of A and B given the following expression. Now the best way to solve this is by first considering the left-hand side of our equation. So let's write this in, and we have 2 times cos of x plus 30 degrees. Now notice here that we can expand this expression using cosine's angle sum identity. So let's do this. So we have 2 times, and we can expand this using cos A times cos B, which is going to be cos of our first angle, cos x, times cosine of our second angle, cos of 30. And because we're using the sum identity, we're going to be using the top operator. And so we have a negative sine A times sine B, which is sine of our first angle, x, times sine of our second, sine of 30 degrees. Now we can simplify this expression by finding the exact values of cos of 30 and sine of 30 degrees. And we can do this using the masterly table. So starting with cosine of 30 degrees, we have going along the cos row and the 30 degree column, we get the square root of 3 divided by 2. And so cos of 30 degrees is just root 3 on 2. So let's make this substitution in. Root 3 on 2. And to find sine of 30, we're going to go along the sine row and 30 degree column, and we're at this value here, which is the square root of 1 over 2, which is just going to give us a half. So sine of 30 degrees is just 1 over 2. Now we can expand our 2 into the brackets, so we're going to get 2 times cos x times the square root of 3 over 2, take 2 times sine x times 1 over 2. And now you can see that our 2's cancel out, so we have a 2 that cancels out here, and also a 2 that cancels out here. And we're left with the following expression, the square root of 3 times cos x take sine x times 1, which is going to be take sine of x. And now you can see here that this is far similar to what the right hand side of our expression looks like. And so we have a coefficient in front of the cos of x, which is just going to be our A value by matching our above expression. And the coefficient in front of the sine of x is going to be our B value, which is going to be this value here. And so now we can conclude that A is going to be square root of 3, and B is just going to equal -1 by matching these terms with our original question. And so that concludes this problem, and now let's move on to another example. For our next example, we want to find the exact value of cos of 75 degrees. Now we only know the exact values of cosine for these following angles. And so what we need to do is find the sum and difference of two of these angles that will make 75 degrees. And in this case, 30 plus 45 degrees will make 75 degrees. And so what we're going to do is change our expression from cos of 75 to cos of 30 degrees plus 45 degrees. And now we can use the angle sum identity for cosine. So we're going to get cos of A times cos of B, which is just going to be cos of our first angle, 30 degrees, times cosine of our second angle, 45 degrees. And because we're using the sum identity, we're going to be using the top operator, which is going to be a negative, sine of A times sine of B, sine of our first angle, 30, times sine of our second angle, which is sine of 45 degrees. And now you can see here that we know the exact values of all of these separate terms. So we're going to make these substitutions in, and we're going to get, starting with cos of 30, going along the cos row and the 30 degree column, we get the square root of 3 over 2. So cos of 30 is root 3 on 2. And to get cos of 45, going along the cos row, 45 degree column, we get the square root of 2 divided by 2. So cos of 45 is root 2 on 2. And for sine of 30, we go along the sine row and 30 degree column, and we're at root 1 over 2, which is just going to be 1 over 2. And for sine of 45 degrees, going along the sine row and 45 degree column, we're at the square root of 2 over 2. So these are all our exact values. And now what we can do is just multiply them together and simplify. So we get our root 3 over 2 times root 2 over 2, take our 1 over 2 times root 2 over 2. And if we multiply these out, we're going to leave these root 3 and root 2 alone. And we get 2 times 2 on the bottom, which is just going to be 4. Take 1 times root 2, which is going to be root 2, divided by 2 times 2, which is 4. And notice here that we can take out root 2 on 4 out of our brackets, and we're going to get the square root of 2 over 4 times root 3 take 1. And so this is our exact value for cosine of 75 degrees. And so that concludes this example, and now let's move on to our final example. For our final example, we want to find cos of A take B, given that sine of A is 15 over 17 and cos of B is negative 4/5. And we're also given that angles A and B are both obtuse angles. Now the best way to start this problem is by first considering what we need to find. And we need to find cos of A take B. And we can expand this out using our angle difference identity for cosine. So let's do that. We get cos of A times cos of B plus sine of A times sine of B. And in our question, we're given that sine of A is 15 over 17. So let's substitute this in. And we're also given that cos of B is negative 4/5. Now, if we find the values of cos of A and sine of B and solve this right-hand side, we will get our solution for cos of A take B. And so in order to find these values, we're going to draw the unit circle. So we have our unit circle here, and the first step is always to draw in our domain. And our question says that our angles A and B are both obtuse angles, and this means that they are between 90 and 180 degrees. And so on the unit circle, 90 degrees is here, and we're going to go all the way around to 180 degrees. So our angles that we're going to be considering are going to be in the second quadrant of the unit circle. So now we want to draw in our angles A and B. And so starting with angle A, we're given the information that sine of A is 15 over 17. And so remember that on the unit circle, sine is always read off the y-axis, and 15 over 17 is close to 1, so it's going to be a value about here. And if we extend this into the second quadrant where our domain is, we get to a point here on the circumference of the unit circle. So let's label this angle in, and it's going to be our angle A. So this angle here is going to be our angle A. And our point up here is going to be 15 over 17. Now the value we want to find in regards to this angle A is this value cosine of A. And remember, cos is always read off the x-axis, and so will be the x component of this coordinate at angle A. And so if we draw our line down to the x-axis, this value here on the x-axis is going to be cosine of A. And the way we can find this value is by considering this right triangle here. And so let's draw this right triangle to the side and see if we can solve for this x value. So on this side we have this right triangle redrawn from the unit circle, and let's fill in the information that we're given. So firstly, we know that this side here, the hypotenuse of this triangle, is going to be of length 1, being the radius of the unit circle. So let's fill this in. And we're also given that this height of the triangle is going to be 15 over 17. And we got this by being given in the question that sine A is 15 over 17. And now we can see that we can solve for this side here of our triangle, and we're going to label it as side x. And we can solve this side by using the Pythagorean theorem. And the Pythagorean theorem states that our hypotenuse squared, which is going to be 1 squared, which is just 1, is equal to our other two sides squared. So x squared plus 15 over 17 squared. Now, if we solve this for x on our calculator, we're going to get two solutions. And our first solution is going to be 8 over 17. And we'll have one more solution, negative 8 over 17. And as we're considering our right triangle with distances, we can't have a negative distance. And so our solution that we're going to consider is the positive version. And so we find that this value of x is going to be 8 over 17. Let's now translate our solution into the triangle in our unit circle. So we found that this distance here, this distance is 8 over 17 units. But as we're dealing with the negative x-axis, we're going to start from 0 and go left towards the negative values, and we're going to go left 8 over 17 units to this point here. So this value is going to be actually negative 8 over 17 units. And so our value for cos of A is going to be the x component, remember, of our angle of A, which is going to be negative 8 over 17. So let's write this in here. So cos of A is negative 8 over 17. So now let's rub this out and leave some room to find our solution for sine of B. In order to find our value for sine of B, we need to label our angle B on the unit circle. So first, starting with our domain, remember our domain is between 90 and 180 degrees, as we're given that angles A and B are both obtuse angles. And we're also given the information that cos of B is negative 4/5. So this means that our cosine value, remember cos is always read off the x-axis, is negative 4/5. And negative 4/5 is going to be about this value here. And let's draw this angle into our second quadrant where our domain is. And so let's draw this angle here. So this angle here will be B. And our value here will be negative 4/5. And so what we need to find is sine of B. And remember, sine is read off the y-axis and will be the y component of our coordinate at angle B. And so if we draw a dotted line out here, we need to find this value on the y-axis. And the way we can do that is by considering our right triangle here. So let's draw this to the side. And now we're going to fill in the information that we're given. So starting with our hypotenuse of our triangle, we know that this will be of length 1, being the radius of the unit circle. So let's write that in. and this distance here will be 4/5 as we start with 0 and we're going left 4/5. So the physical distance will be this value 4/5. And now you can see that we can solve for this height, which is going to give us the y component here, which will be sine of b. And so let's label this height as y, and we can solve this by using the Pythagorean theorem. And remember, the Pythagorean theorem states that our hypotenuse squared, which is 1 squared, which is just 1, is equal to the sum of the squares of our other sides. So y squared plus 4/5 squared. And if we solve this on our calculator, we're going to get two solutions. We're going to get one solution being y is equal to 3/5, and our other solution will be -3/5. And remember, because we're dealing with distances, we can't have a negative distance, so we're going to disregard our negative solution, and so our solution for y will be 3/5. And so our height here we have found to be this value. Now, translating this solution into the unit circle, we found that this height here was 3/5. And so if we start at 0 on our unit circle and go up along the positive y-axis a length of 3/5, we're going to get to our point here, which is going to be 3/5. And so because we're dealing with the positive y-axis, we're going to have a positive value. And so we are now shown that the y component of b is this value 3/5, showing that sine of b is 3/5. So now we have all the information we need to solve for cosine of a take b. So let's rub this out and leave some room to finish off our example. So we've shown that cos of a take b is equal to cos of a, which we found to be -8/17, multiplied by cos of b, which was given as -4/5, plus sine of a, which was given as 15/17, times sine of b, which we found to be 3/5. And so now we can solve this right hand side on our calculator, and if we solve this on our calculator, we're going to get a solution of 77/85. And so we have shown that cos of a take b is this solution here, 77/85. So that's going to conclude this video, and in the next video we're going to derive the angle sum and difference identity for sine.